In mathematics, we like to classify numbers in terms of what kind of numbers they are. And we'll start with the basics. And where we're going to use this is, it's theory essentially. We're going to use it when we are told what kind of answers to expect in a question. Okay, so it's one of the few things you can learn off by heart in mathematics. So enjoy being able to do that. Okay, we're going to first divide into two categories, which is rational numbers and at the bottom here, irrational numbers. Okay, and in the category of rational numbers are all of these types of numbers. But the distinction between rational and irrational is going to be one of the most important ones that we do in this section. Okay, natural numbers you will remember as a double bar N, like that. And it's all the ones that you would have worked with from the time you learned to count. It's a set of numbers that goes 1, 2, 3, and it goes up in units of 1 into positive infinity. So natural numbers are the ones that are the counting numbers. So always imagine yourself at 2 or 3 years old counting. Where did you start? Not with 0, but with 1. And then all we do when we add on the whole numbers, it's just natural with a 0, is that it's exactly the same thing, but it starts with 0 and carries on like that. And you probably remember at some point understanding that 0 was a thing, and you would have done that a little bit after you learned how to count. Integers are very much like whole numbers, okay, but also negatives. But it's negative whole numbers. And I want you to be aware of that because you have come across these concepts before. And sometimes people think that every time they see a negative, it means that it is an integer, and it's not. An integer is your z, and it includes, so dot, 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 from negative infinity, let's go negative 2, negative 1, 0, 1, and 2, okay? The important part is that it is negative and positive whole numbers. So, for example, negative 2.5 is not an integer. It's negative, but it's not an integer. Okay. Common fractions you've been dealing with since, I think, grade 3 onwards. And your common fractions will be anything where it is an a over a b, where a and b are both integers. Okay, so I'm just rephrasing this in a new way that's going to be useful this year. So where a and b are integers, because of course you can get negative fractions, but I'm saying it's a common fraction only if you have like a whole number there, could be negative, a whole number there could be negative. Okay, so a and b need to be integers in order for it to be classified as a common fraction. Okay, remember that all of these things in this list of bullets are classified as rational numbers. With decimal fractions, you get ones that end. Okay, and they may take a really long time to end. So I'll give you a silly example, 0.1, 2, 3, 4, 5, 6, 7. It does actually end, and I know that because there's no dot, dot, dot coming. Okay, so I know that it has an end to it, which means it could be written as that whole number over 1 with that number of zeros, right? In the same way that 0.1 can be written as 1 over 10 to help you understand the concept. So a terminating decimal could actually be written as a fraction, could actually be done. And that's something we're going to come back to quite shortly. Recurring means repeating. There will be a pattern. And you've seen that on the calculator before. You've seen that a third gets you 0.333. Here I'm putting a dot, dot, dot. It doesn't terminate, right? This is a non-terminating decimal, but it is recurring. Other examples we can get is, for example, 1, 2, 1, 2, 1, 2. And I can put my dot, dot, dot to show that it continues this pattern. And now we're going to look at the irrational numbers. Okay. So we just talked about terminating. Now I'm saying non-terminating. So that obviously means it never ends, right? So we're talking about a never-ending decimal. Non-recurring decimal, so non-repeating, no pattern. Okay, so this means that decimals do not end. I'm just finding new words for the same thing, okay? And they do not repeat. Because if they do, they are rational, okay? Because that's back in this category over here. These guys are rational, the ones that terminate and the ones that recur. So they're irrational if they do not end, and they also do not repeat. Okay, so non-perfect square roots and non-perfect cube roots. So type this into your calculator now. I know that 2 is not a perfect square. I actually also know it's not a perfect cube. So type that into your calculator and you will get a number that goes on and on forever and does not repeat. So if you try to square root something, that's not a perfect square. Or if you try and cube root something, that's not a perfect cube, and so on with all the different kinds of ways in which you can root numbers, you will always get an irrational answer. Okay, real numbers consist of all of the above. Okay, that's the last category. So that would be my rational, which is a cube, and also my irrational, which is a cube with a little apostrophe. Just a word then on non-real numbers. Have you ever tried to do that? Then you get a math error. So often a non-real number will come up with a math error. It could also just be you've typed it in incorrectly. That would be considered non-real. Another one that you've come into contact with by now is when you put something over 0. It'll also come up with a math error, but that is because it is undefined, as in we have no definition for things over 0. I'm going to do a little Venn diagram for you of the way the number system works, so that you understand how things are included and excluded. You do not need to be able to draw this Venn diagram. It is just a way to help you visualize how the numbers get categorized. Okay, so in my real number system, all right, so all the things that are real, that's my big R, I've got all of the real numbers. Okay, so there's a big bubble including all of them. Okay, and then there's a smaller category because there's not much to put in there, but all categories are infinite, which can be a bit confusing. I can also talk about my non-real numbers. Okay, so things like square roots of negative. So that is a separate bubble. And the reason I'm showing it to you in this way is because I want you to understand that a number can't be real and also non-real. It also can't be rational and irrational. So I'm going to make a bubble inside real. And this bubble is the bubble of rational numbers, okay, which gets the little q. And then I'm going to make another bubble over here. It's still inside the real number system, but these are the guys that are irrational. Okay, and I'm going to fill in the ones that are rational first. Remember that rational is categorized as all those bullet points we were looking at earlier. And so rational is going to be your fractions, a over b, where a and b are both integers. It's also going to be your recurring decimals. And it's going to be your terminating decimals. Okay. But it's also going to be rational numbers also include, so you can see the bubble is within the rational bubble. So these are the kinds of decimals and fractions we're dealing with, but it also includes all the integers. So rational numbers include the integers, okay, which includes the whole numbers, which includes the natural numbers. So I'm going to put those in now. Okay, so my integers will be my -1 and 0 and 1, and my whole numbers include the 0, 1, 2, and and so on. And my natural numbers start at 1 and go 1, 2, 3. For my irrational numbers, which are still considered real, I have my non-terminating, non-recurring decimal. Dot, dot, dot. Okay, so it's non-terminating, non-recurring. Okay, and also in that category would be things like the square root of 2, or maybe the cube root of 7, and so on. I hope that helps you understand how to categorize the different kinds of numbers that we get. So one of the most important ways that we're going to categorize numbers is this idea of rational versus irrational. Okay, so just a reminder then that rational gets a Q and irrational gets a Q with a little apostrophe. Okay, so you're going to need your calculator for this one, please, because it really helps with the way that things are displayed on the screen to tell whether something is rational or irrational. Okay, so 3 is a number that is a whole number, it's a counting number, it's like right in the middle of that Venn diagram. It's definitely going to be a rational number. Okay, your other test for rational is, can it be written as a fraction? Absolutely, 3/1. So yes, that number is rational. For question B, -8 is an integer. Could that be written as a fraction? Yes, -8/1. Okay, I think these ones are quite intuitive. Now, question C is written as a fraction, where both the top and the bottom are integers. So yes, it's also going to be rational. 0,1 is a decimal, but what kind of decimal is it? Does it terminate? Yes, because there's no ... afterwards. So it terminates, it actually finishes, it ends, therefore it is rational. But what about this one? 0,03. There's 2 decimal places, but there's no ... So it also terminates, and when it terminates, it is rational. Question F has a whole bunch of numbers followed by an ellipsis, a bunch of dots. Can you see a pattern? So I can see it's non-terminating, but is it non-recurring? And I see no pattern there. Because there's no pattern and it doesn't end, this one would be irrational. Okay, here you're going to use your calculator. If you type in root 9 into your calculator, you're going to get 3. Okay, and I would recommend writing that down in order to then assess whether it's rational or irrational. And you know that that's rational. Okay, so it's always a good idea when a number is given to you in a form factor that you can't quite see, then go and type it into your calculator. Now root 15, you type that into your calculator, you're going to get a whole long decimal. How do I know that? Well, I know that 15 is not a perfect square, and so I know that that's going to be irrational. What about the cube root of 8? Well, when I type that into my calculator, I get 2 out. Or you might have known that off by heart, which means it's a totally normal number, it's natural, and a natural number is always going to be a rational number as well. The cube root of 25 would be fine if 25 was a perfect cube, but it's not. And you're going to get a really long, non-terminating, non-recurring decimal here. So you can write that out if you want to, or you can just see it on the calculator and realize, hey, this decimal is non-recurring, non-terminating, and therefore the cube root of 25 is irrational. What about the cube root of -64? You might not be sure about this one, but if you type it into your calculator, you're going to find that you get -4 as your answer. -4 is an integer, and an integer is perfectly rational. 0,3 recurring. Okay, this is an interesting one. Please really do type this into your calculator now, and I want you to type in 0,3, 3, 3, and just keep on going for 15 places. Okay, and what you'll get is that that is actually, when you press equals on your calculator, you're actually going to get a third, which is a common fraction, right? Which means it's rational. But there's another way in which you can tell it's rational, and that is that this thing is recurring. The 3 repeats itself, and that makes this a rational number. One of the applications of understanding a rational versus an irrational number is when you are asked to find a rational number between two other rational numbers. Okay, so what we're going to do here is we're going to use our primary school skills to find an LCD between these two numbers. Okay, so I want to have them in a way that I can compare them. So with 5 and 3, an LCD would be 15. Okay, so I'm going to put them both over 15. So 3 over 5 is going to change to something over 15, and 2 over 3 is going to change to something over 15. I want to remind you then that 3 over 5, to get it over 15, I'm going to times the bottom by 3, and what you do to the bottom, you do to the top. So that is 9 over 15. 2/3, if I change that, I've got to times by 5 at the bottom to get it to 15, so I times the top by 5, and that gives me 10 over 15. Okay, but I'm supposed to find a number between them, and the thing between 9 and 10 would be 9.5, or 9 and various other fractions, and that's not going to give me a rational number, because I need to find something that has a fraction where the top and the bottom are both integers and not fractions. You can't have a fraction within a fraction and then call the whole thing rational. It needs to be rewritten. Okay, so my LCD wasn't quite enough. What if I find another denominator that's a bit higher? Let's double that denominator. Let's go with 30. So let me put 9 over 15. Let me put that as a number over 30. And let me work with that one instead of the original, because I'm just doubling everything, right? So I'm doubling the 9 as well. So it's actually 18 over 30. And what about 10? 10 would be 20 over 30. Right, now I can see that in between those, in between 18 over 30 and 20 over 30 would be 19 over 30. 19 over 30 is between 3/5 and 2/3. Let me show you how to write that quite nicely. I'm going to say 3/5 is less than 19 over 30, which is less than 2/3. And that just puts it in a way that shows that this number falls in between the others. Okay, now we're going to work with irrational numbers. Between which two consecutive integers do the following irrational numbers lie? Now, these questions must be done without using a calculator, both these ones and when you're finding a rational number between two other rational numbers. So that means you need to show all of your steps. Of course, you can just go and type this in and see that it is something comma something, and you can figure out which integers it lies between, but that's not what we're asking you to do. We're asking you to find two numbers on either side of this that actually are perfect squares. So that revolves around you remembering all your perfect squares, because we're dealing with square roots, so we're only going to get integers when we have numbers that are perfect squares. So let me remind you, 1 is a perfect square, 4 is a perfect square, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. Now, if you don't know those off by heart, you could work them out on a calculator, but you're going to need to do the rest of the steps on your own. Okay, so what is on either side of 11? Which of these perfect squares is on either side of 11? Well, it's going to be 9 and 16, so we're going to write it using our less than and greater than signs. So 9 is less than 11, which is less than 16, and of course what we want is we want the square root of each of those. And I know the answer to the square root of 9, it's 3. Root 11 is irrational, so I leave it as a root. Root 11, which is less than the square root of 16, which I know is 4. And therefore my answer is between 3 and 4. Okay, and what when it's negative? So let's go back here and let's look at my perfect squares. Between which two does 6 fall? Between the 4 and the 9, but of course it's negative, right? So we're going to be working the other way around. So I'm going to say negative root of 9. I can't put the negative inside, otherwise I have a non-real number. Negative root 9 is less than negative root 6, which is less than negative root 4. Then I can get my answers here, which will be negative 3. This I don't have because it's irrational. And this one will be negative 2. So then my answer will be between negative 3 and negative 2. If we look at my last two examples where I've got to use the pi button, the rest of it needs to be done without using a calculator, but unfortunately when there's a pi button involved, I'm going to have to use the calculator. So I'm going to type that into my calculator, and I'm going to type in the fraction pi over 2. And I'm going to put a squiggly equal sign which says is more or less equal to 1,57. Okay, and that is just rounded off to 2 decimal places. But the next step I'm going to need to do on my own. I'm going to need to say that is between 1 and 2. So 1 is less than pi over 2, which is less than 2. And the same for negative 3 pi. That is more or less equal to negative 9,42. So therefore it is between negative 10, and remember now we're working backwards on the number line, negative 9.